Okay, let's start. So you had a question or some, maybe several questions. Happy to answer as many questions as you have. So go ahead. Which one should I do?
Yes, number 2 from exercise 1.4, please. That's page 38 on the note.
Actually, so this is on Gaussian elimination.
Yes, that's correct.
Okay. Exercise 2. Just 1 second. Okay, just to prove the equivalence of two systems of equations. Is that correct?
Yeah.
Okay, so this is section 1.4, number 2, and we have a system of equations x minus y equals 0 and x plus z equals 2. So that's two equations in three variables. And we have another system, x plus y plus z equals x plus y plus 2z equals 4. 2x minus y plus z equals 2. And 7x minus 2y minus 5z equals minus 10. So to say these systems are equivalent means that they have exactly the same solutions. So I guess one thing we could do is just solve each system. So let's start with this system. Let me make sure I wrote it down right. X plus y plus 2z equals 4. 2x minus y plus z equals 2. 7x minus 2y minus 5z equals minus 10. Okay. So I'm going to start with this system and use Gaussian elimination. So my first equation, x starts with a coefficient 1. That's good. So x plus y plus 2z equal 4 is the first equation. If I take the second equation and subtract 2 times the first equation, that gets rid of the x. So I get 2x minus 2x is 0. Minus y minus 2y is minus 3y. Z minus 4z is minus 3z. And 2 minus 8 is minus 6. That's the new second equation. And let me get rid of the 7x from the third equation. I'll take the third equation minus 7 times the first equation. So 7x minus 7x is 0. Minus 2y minus 7y is minus 9y. Minus 5z minus 7 times 2 minus 14. Minus 5z minus 14z is minus 19z equals minus 10 minus 28 is minus 38. Right? Does that look okay? So it's minus 7 plus this, minus 7 plus this, minus 14 and minus 5 is minus 19, minus 28 minus 10 is minus 38. All right, that's what it seems to be. If I take x plus y plus 2z equals 4, In this equation, if I divide by -3, it becomes y plus z equals 2. And this is still minus 9y minus 19z equals minus 38. And now I can get rid of the y's from the first and the third equation. So the second equation I'm not changing. If I take the first equation minus the second, I get x, y minus y, 2z minus z is z, and 4 minus 2 is 2. And if I add 9 times this equation to the bottom equation, 9y minus 9y is 0. 9z minus 19z is minus 10z. And 9 times 2 is 18. So 18 minus 38 is minus 20, I think. So this is x plus z equals 2. Y plus z equals 2. If I divide this by minus 10, I get z equals 2. Which means what? Z is equal to 2. If z equals 2, y equals 0. And if z equals 2, x equals 0. So it looks like this is the unique solution to the second system of equations. So this system of 3 equations and 3 unknowns only has one solution. What about this? If we want to solve the system x minus y equals 0 and x plus z equals 2, I can eliminate x from this equation by subtracting the first equation from the second. So x minus y equals 0. X minus x is 0. 0 minus y is y. Z minus 0 is 0 equals 2. And if I add the second equation to the first, I get x plus z equals 2. So it may be these systems aren't equivalent. So for any value of z, x is equal to 2 minus z, y is equal to 2 plus z, and z is equal to z. So it looks like for the first system of equations, x, y, z is going to be 2, 2, 0 plus minus z, 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 which is 2, 2, 0 plus z times the vector minus 1, 1. Let me just check. So 2 minus 2 is 0, and 2 plus 0 is 2. So this is a solution, a particular solution to the inhomogeneous system. And minus 1, 1, 1, minus 1, 1, 1, minus 1, minus 1 is 0, and 1 and minus 1, sorry, minus 1 minus 1 is not 0, so something minus 1, 1. Let's see. Let me just double check what's going on here because something doesn't look right. We have x minus y equals 0, x plus z equals 2. So if I want to solve this by Gaussian elimination, first I eliminate the x. So I get x minus y, and then x minus x, 0 minus y plus z equals 2. And then if I eliminate the y
Professor,
here, that's what I want to
we
do.
cannot see what you're writing on top.
I get x plus z equals 2. So x equals 2 minus z, y equals 2 minus z, and z equals z. So a solution is 2, 2, 2 minus z. So minus 1, 1. So minus 1 plus 1 is 0, and minus 1 plus 1 is 0. So this is the general solution for the first system of equations. And for my second system, this is a particular solution, and minus 1, 1. So it may be that I should have said prove the equivalence or inequivalence, because if I did this correctly, the two systems are not equivalent. So let me just look at this first. The second system was x plus 2y, x plus y plus 2z equals 4, 2x minus y plus z equals 2, and 7x minus 2y minus 5z equals minus 10. So for this system, 2, 2, 0 is a particular solution. Right? If you put in 2, 2, 0, this is 4. 2, 2, 4 minus 2 is 2. 14 minus 4, oops, is that right? 2, 2, 0. 14 minus 4. Yeah. So whatever it is, I must have made some typographical error. So so this is definitely the solutions for the first system. And 0, 0, 2 is a particular solution for the second system. But it looks like for the second system, that's the only solution. 0, 0, 2. Yeah. So somewhere in that problem, there's a typo. Thank you. But the way you solve a problem like this, in any case, is you solve each system of equations and you find the general solution. And if it is, in fact, the case that both systems have the same solutions, then the systems are equivalent. And if not, they're not equivalent. That's the whole story. But I will see whether I have a plus sign instead of a minus sign somewhere that screwed everything up. I think it should have been for the last equation, 7x minus 2y plus 5z equals minus 10. I think I should have put a plus sign, a plus sign instead of the minus sign. So equals plus 10. I think that's what it should have been. I'm not sure how it got screwed up. In any case, all you're doing is solving systems of equations and comparing the general solutions. Right? Other questions?
I have one for and I guess it's just like a clarification question for number 5 on page 30, where it says prove that the intersection of a set of subspaces of a vector space is also a subspace of the vector space. Would I be okay like if I use actual numbers or like a previous example and showed how that the intersection was also a subspace? Like,
So, right, no. So that definitely is not enough. So when you have to prove something, it's always useful to look at concrete examples just to give you an idea of what to do. But if it says to prove a general statement, you have to prove the general statement. So this is in section 1.3. Is this number 10?
Number 5.
Number 5. So prove the intersection of subspaces is a subspace. And just to get an idea of what to do in the general case, let's start with 2 subspaces. So let W1 and W2 be subspaces, let's say, of a vector space. And for us, a vector space so far is just Rn for some dimension n. So we know that because these are subspaces, so what is the intersection? W1 intersect W2. So this is the symbol for intersection. This is the set of all the vectors in the vector space which belong to both of these subspaces. W is in W1 and W is in W2. So what do we know about subspaces? A subspace must contain the 0 vector. So 0 is in W1 and 0 is in W2. So that means that 0 is in W1 intersect W2. So this intersection contains the 0 vector. Then suppose we let W and W prime be 2 vectors in the intersection. So that means these 2 vectors are in both of these subspaces. W is in W1 and W prime is in W1. And also W is in W2 and W prime is in W2. But if W is in W1 and W prime's in W1, because this is a subspace, W plus W prime is in W1. And because also W and W prime are both in W2, W plus W prime is in W2. And because W plus W prime is in both of them, it's in the intersection. So the intersection of 2 subspaces is closed under addition. Right? I mean, you have to remember there are 3 conditions for a subset of a vector space Rn.
Yeah.
To be a subspace, it has to contain 0, has to be closed under addition. It also has to be closed under scalar multiplication. So we need to check scalar multiplication. So let W be any vector in W1 intersect W2, and let C be any scalar, some real number, R, in R. So if W is in W1 intersect W2, W is in W1, which is a subspace, so C times W is in W1. And if W is in the intersection, W is also in W2, which means C times W is also in W2. So CW is in both of these. So CW is in the intersection. That means the set is closed under scalar multiplication. So this proves, we just proved that if you have two subspaces, their intersection is also a subspace. And you can prove it for more, but this is the basic idea. This is the thing you have to keep straight.
Okay,
Just giving concrete examples is not a proof.
How were we able to, like, is it just commonly accept because we let C be in R, does that?
So
Like,
what you have to show is that for every vector W
yeah,
in
that's
the
it.
intersection,
Uh-huh.
and for every scalar C,
Yeah.
C could be 10, 100, pi, a million, for every number C, CW is in this intersection for every scalar C. So just let C be any scalar. Yeah, if you write down C equal 2 or C equal 13, that's not enough.
Okay.
Right. Any other questions I should do?
For me, page 20, problem 5.
Let me take a look. Okay. So let me just make sure I'm looking at the same. So this is section 1.2, number 5.
Yes.
And we're looking at the equation 2x minus 8y minus 6z equals 0. Is that correct?
Yes, that one.
Okay. So we want to find all solutions. The simplest thing is just to divide by 2. So gives us smaller numbers and the coefficient of x is 1. So x minus 4y minus 3z is 0. So whenever you have a solution, x is going to be equal to 4y minus 3z. So if you have any solution x, y, z, a solution, x is really 4y minus 3z, y, z. And I can think of this if I like. There's no reason to write this out like this, but I'm just doing it to make it clearer. This is like y plus 0 times z, and this is 0 times y plus 1 times z. So this is like, if I write this as a sum of two vectors, this is 4y, y0 plus minus 3z, 0, 1 times z, which is y times the vector 4, 1, 0 plus z times the vector minus 3, 0, 1. Let me just double check something. Oh, this should be a plus 4y plus 3z. Yep. So what this says is the solution space of the equation is W equal all scalar multiples of 410 plus any scalar multiple of 301. That is all linear combinations of the two vectors 410 and 301.
Oh, okay. Thank you, Professor. I was just wondering one more thing. Right below problem 5, so right below problem 5, there's another problem, and like it has like 3 sections, A, B, and C. For section A, it says prove that W is a subspace of R3. Like I was wondering, how do you approach proving like proving that? Because it also has an equation right next to it.
Well, so we proved the theorem in the course that the set of all linear combinations of any set of vectors in Rn is a subspace of Rn. And in this case, n equals 3, and we have the vectors 4, 1, 0 in R3, and the vector 3, 0, 1 in R3. And W, the solution space, is the set of all linear combinations.
Oh, so that's what it means. Like when it says that proof W is a subspace of R, we just need like to show that with the
And
solution.
what I wrote about a basis and the dimension, I'm going to take that out because I haven't defined those things yet.
Oh,
Oh, great. I was actually going to ask about that. It had that tonight. So I was like, I don't know what a basis is.
Right. No, I haven't defined it yet. So that shouldn't be there.
Thank you.
Okay. Any other questions about homework?
this is not about a specific problem. I just want to know, like, because you said like you are willing to accept late homeworks last night. I mean yesterday. But like, how late is like the maximum before you put out the cutoff, before you stop accepting it?
When I give the day of the final exam.
Oh, okay.
It's just that if you wait until the end of the semester to try to do the homework, and it's too much. You have to sort of keep up. It's hard for you. And you certainly won't do well on the exams before that. So the more you can stay on schedule, the better.
Yeah. It's just because it's a lot of homework. I just realized that I couldn't do everything in one day, so I just like wanted to know, like, you know.
No, that's fine. And if you can't do everything, you can't do everything. That's perfectly normal.
Okay, thank you, Professor.
Right. So I wanted to every day in these sessions, I like to prove something new. So let me go on to what is in the current set of notes, section 1.6, though I'm in the process of revising the notes, so this will really be part of the previous section. So what I proved this morning from section 1.5 is the following theorem. So we have a homogeneous system of linear equations where we have m equations in n variables. And the theorem says that if n is bigger than m, if you have more variables than equations, then the system it always has the zero solution, but it also has a non-zero solution. Right? And that is a very important fact. So remember, we've defined a linear combination of vectors. So if v1 up to vk are vectors, let's say in Rn, and c1 up to ck are scalars, then I can take the ith vector v sub I and multiply it by the scalar c sub I. And I do that for I going from 1 up to k. I have c1 v1 all the way up to ck vk. And if I add this all up, this is the definition of a linear combination of the vectors v1 up to vk. So a linear combination of a finite set of vectors is just some vector that you get by multiplying each of the vectors in the set by a scalar and adding them all up together. You can also notice the following. If v is any vector in Rn and you multiply it by the number 0, let me just emphasize this is a vector, you get the 0 vector. Right? Because scalar multiplication, you multiply each coordinate, like 0 times v, that's 0 times the vector x1 down to xn. So you're multiplying each coordinate by 0, and you're just getting zeros. So in particular, if you take vectors v1 up to v sub k, and you multiply them all by the number 0, this is just the 0 vector added to itself, and you just get the 0 vector. So if you take a linear combination of vectors with all the coefficients 0, you get 0. You get the 0 vector. So that's a very simple observation, but it's important for the following definition. So we say that a sequence of vectors v1 up to v sub k, so the order is important and they're not necessarily distinct. We say that these vectors, the sequence is linearly dependent if there exist scalars, numbers, c1 up to ck, not all 0. Some of them can be 0, but they can't all be 0, such that c1 v1, this linear combination, is the 0 vector. So if there's a linear combination of vectors, of your vectors, with the coefficients not all 0, and that linear combination equals the 0 vectors, then the vectors are called linearly dependent. And vectors are linearly independent if they are not linearly dependent. So that's kind of obvious. So vectors are linearly dependent if some linear combination of them is 0. So for example, let's say we're in R2, just two-dimensional vectors. Suppose V1 is 6 minus 14, and V2 is minus 15, 35. So if you take 5V1, that's equal to 30 minus 70. If you take 2V2, that's multiply each of these by 2, you get minus 30, 70. So then you'll notice 5V1 plus 2V2 is the vector 30 minus 70 plus the vector 30, 70. When you add coordinates, you get 0, 0. So therefore, these vectors, this is a linear combination equal to the 0 vector, and the coefficients are 5 and 2. They're not both 0. So therefore, these vectors are linearly dependent. Suppose we take in R3, suppose we let E1 be the vector 1, 0, 0, E2 be the vector 0, 1, 0, and E3 be the vector 0, 0, 1. I mean, geometrically, it's like in three-dimensional space, these are the unit vectors in the x, y, and z directions. So suppose we have scalars x1, x2, x3 in R, and x1, e1 plus x2, e2 plus x3, e3 is the 0 vector. So what does that mean? The 0 vector is 0, 0, 0. That's x1 times 1, 0, 0 plus x2 times e2, which is 0, 1, 0, plus x3 times e3, which is 0, 0, 1. If I scale or multiply and add, I get x1, x2, x3. So if this linear combination is 0, x1, x2, x3 is 0, 0, 0, that means all of these numbers is 0. So the vectors e1, e2, e3 are linearly independent. Because the only linear combination of them that gives 0 occurs when x1, x2, x3 are all 0. You can't have a non-zero number there.
Professor, I just want to bring to your attention that in page 11, problem 6, we have a problem exactly like that using that same exact idea.
Yep, that's true. Well, problem 5 is similar to this. Problem 6 is different.
Right.
Yeah, that's true.
Professor,
Yeah.
can you go back just for 1 second to the last page? Hold on 1 second. Can't see it. All right. Thank you.
Okay. So there's an important fact about linearly independent vectors, which is the following. So this is a theorem. Let v1, v2 up to v sub k be a sequence of linearly independent vectors in Rn. If we have two sets of scalars, x1, x2 up to x sub k, and y1, y2 up to y sub k, so these are scalars, these are real numbers. And if we take the linear combination x1, v1 plus x2, v2 up to x sub k, v sub k, this is one linear combination of v1 up to vk. And I can take another linear combination using the y scalars, y1, v1 plus y2, v2 up to y sub k, v sub k. If these linear combinations are equal, then in fact the scalars have to be the same. x1 equals y1, x2 equals y2, up to xk equals y sub k. That's the theorem. And how do we prove it? So the proof is very nice. It just uses the definition of linear independence. If x1 v1 plus x2 v2 up to xk vk equals y1 v1 plus y2 v2 up to yk vk, if this is true, then if you subtract you get 0. But here I have x1 v1 minus y1 v1. This is the same as x1 minus y1 times the vector v1. x2 v2 minus y2 v2, that's just x2 minus y2, that's scalar times v2, all the way up to xk minus yk vk equals the 0 vector. But v1, these vectors, v1, v2 up to v sub k, linearly independent, what does that mean? It means the only linear combination of the vectors that gives you 0 occurs when all of the scalars is 0. That means x1 minus y1 equals 0, x2 minus y2 equals 0, up to xk minus yk equals 0, or in other words, x1 equals y1, x2 equals y2, xk equals yk. So if one linear combination of the vectors v1 up to vk is another linear combination, in fact, it's exactly the same linear combination. The coefficients have to be the same. Right? So that's a basic fact. And the reason why this comes up right now is it uses the theorem about linear equations with more variables than equations, a system of linear equations with more variables than equations. So this is the fundamental theorem for this afternoon. It says the following. suppose you have positive integers, m and n, and m is less than n. So you take, it says every sequence of n vectors in Rm must be linearly dependent. So if you're looking at m-dimensional vectors and you take n of them and n is bigger than m, those vectors must be linearly dependent. That's what this theorem says. So suppose, so how does the proof go? So take n vectors. Say v1 is the vector a11 down to a m1. And v2 is the vector a12 down to a m2, and so on. V sub m, the nth vector, sorry, v sub n, the nth vector is a1n down to a mn. So here we have n m-dimensional vectors. And suppose you have scalars, or so consider taking a linear combination x1 v1 plus x2 v2 up to x sub n v sub n, and we want to find scalars x1 up to xn where this is equal to the 0 vector. And to show that these vectors are linearly dependent, mean I can find x is not all 0. So let's just write this down very explicitly. x1 v1, that's x1 times the vector a11 down to a m1, plus x2 times the vector v2 a12 down to a m2, all the way up to x sub n times the vector vn, which is a1n down to a mn. And that's supposed to be the 0 vector. Now, if you scale or multiply, this is just this times this. I'll write it as a11x1 down to am1x1. And this is, these should be a's. This is the vector a12x2 down to am2x2. And this last vector is a1nxn down to amn xn equal to the zeros. When I add these vectors up on the left, I get a vector where the first coordinate is a11x1 plus a12x2 up to a1nxn. The last coordinate will be am1x1 plus am2x2 up to amnxn equals the vector with all zeros. So this linear combination of the vectors gives you the 0 vector, is equivalent to saying that's the solution of this system of m equations in n variables. What we have here is m, this is a linear system of m equations in n variables. And we proved the theorem, I proved the theorem this morning in section 1.5. If you have m linear equations in n variables, homogeneous, that means all the right-hand sides are 0, and we have more variables than equations, there exists, just one second. Sorry. If you have m equations and n variables, and n is bigger than m, more variables than equations, so by the theorem, there exist scalars, x1 up to xn, not all 0, that solve these equations. But that's equivalent to x1 v1 plus x2 v2 plus x sub n v sub n is the 0 vector. So v1 up to vn are linearly dependent. That's what we wanted to prove. So it turns out this is perhaps the most important theorem in all of linear algebra. It's just a theorem about linear equations, homogeneous systems of linear equations, and this consequence. But yeah, it's a very interesting theorem. So it's worth spending some time thinking about this.
So for when it's linearly dependent, that's when the result or the solution winds up with us having the 0 vector.
When so vectors, so we're interested in linear combinations of a set of vectors equal to the 0 vector. And if you take all of the scalars equal to 0, you will always get the 0 vector.
Yeah.
The question is whether there's any other choice of scalars. So if there's some other choice of scalars, not all 0, that gives the 0 vector, the vectors are called linearly dependent. And if not, they're linearly independent. So we saw an example with those unit vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. Those vectors that I called E1, E2, E3, they are linearly dependent. And we also saw a pair of vectors that those were linearly independent. But we also saw some vectors that were linearly dependent. And yep.
Yeah, the ones that were linearly independent,
that's like the opposite. You have a set of vectors. They're either dependent or independent.
Yeah.
So it's one or the other, but not both. So I define linearly dependent. And if the vectors are not linearly dependent, then they are linearly independent.
Right. I think what I'm asking is like, for that example, when you showed us that the vectors E1, E2, E3 were linearly independent, was that because if you were to sum those together, you'd get a non-zero solution?
No, it was. Let me go back and see if I can find the pages.
Yeah. Oh, I think there's one before that one. Oh, before that one. It was the one where you had that little thingy to the side, like the 3 vectors drawing.
Right. Yeah. Here it is.
Okay.
So
yeah,
here are the 3 vectors.
Yeah.
This is the x-axis, y-axis, z-axis, and these are just like the unit vectors in the 3 directions. If I take a linear combination of them, it's this exactly. And when you expand and add this all up, this is the vector x1, x2, x3. And if that's equal to 0, 0, 0, then all of these numbers are 0.
Hmm.
So that means the only linear combination that gives the 0 vector occurs when every one of the scalars is 0.
Obviously, it would have to be 0. Okay. Okay. But I guess I'm okay. So, oh, okay. But the E1, E2, and E3 are linearly independent because they have the one inside of it, right? That's why they are.
No, they're linearly independent because the only linear combination of them that gives the 0 vector
Excellent.
occurs when all three numbers are 0, x1, x2, x3 are 0.
Okay. So if let's say, for example, right, the E1, which is 1, 0, 0, if that one wasn't there and instead it was 0, right, would we still be able to say that E1 is linearly independent?
No, it's
Right.
a different vector in a different situation.
Hmm?
Here, let me give another example. Suppose I'm in R2. I take the vector v1 to be 1, 0, v2 to be 0, 1, v3 equal to be 1, 1. So
Okay.
these vectors are dependent, not independent. Because if I take 1 times v1 plus 1 times v2 plus minus 1 times v3, I get the 0 vector.
Oh, you're adding them. It's a linear combination. Duh. Okay. 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 Okay, that makes sense.
Oh, okay. But I mean, there's a lot to think about. There's not a lot to write necessarily, but these are concepts that you have to become familiar with.
Okay, and then really quick, one more. So there was a theorem, there was a theorem after that, right? And then you had a proof, and the proof was talking about how basically like when you subtract it, you would get 0, and then that made the x1 equal to the y1, or xk, I guess, equal to yk. The coefficient's the same.
Right. The theorem said that if you have linearly independent vectors,
Yeah.
this was the theorem.
Mhm.
If you have linearly independent vectors, so the important thing is independent, and if one linear combination equals another linear combination, that only can happen if the numbers are the same. X1 is Y1, X2 has to equal Y2, and so forth.
Yeah.
And I proved that by just subtracting this vector from this and getting a linear combination of the vectors equal to 0.
Okay. Alrighty, thank you.
Sure. Anything else before we go?
Not from me.
Okay. I'll be back tomorrow morning, and I'll be back tomorrow afternoon. All right. Take care, all.
All right, bye-bye.